Hello everyone, so welcome to my video on differentiation properties. We're going to begin with an easy one, the constant rule. So the derivative of any constant is 0. So essentially, if your function f of x equals c, this implies, implication arrow, f prime of x is equal to 0. Let's go ahead and prove that statement. So the proof, we know that the function is equal to c, and we know f prime of x. We want to show that f prime of x is equal to 0. Well, remember the definition. What is f prime of x? F prime of x is the derivative. We're going to use the limit definition of a derivative. So the limit as h goes to 0 of f of x plus h minus f of x over h. Okay. To make this a bit easier, let me sketch a drawing. Whenever you're doing proofs, do not base it off a drawing. You can use a drawing to guide your thoughts, but do not use just a picture for a proof. That's definitely an issue. But just to have an idea of what we're doing, it's good to use a picture as a guide. So if this is a function, it's a constant function at c, and we know f of x is c. So any x value you take, let's take x over here, it's going to hit the function here at c. Over here we have f of x plus h. So if we shift over by h, so from this x we go to this point here, x plus h, what's f of x plus h? What value will we hit? It's also c. So over here, just remember this is f prime of x. So I should have started with f prime of x. F prime of x equals, this is our definition, the limit definition of the derivative, and it's equal to the limit as h goes to 0. And as we saw, f of x plus h from our drawing is over here, which is our value of c, minus f of x, which is also hitting the function, the green function here, which is also c over h. C minus c is 0, so limit as h goes to 0. C minus c is 0. There's no h in here because the numerator was 0. That canceled everything out, giving us 0. And this completes the proof. Okay, so very simple proof, showing us that the derivative of any constant is always 0. Let's look at a couple of examples, quick examples. So very simply, if I'm given the function f of x equals 5, what's our derivative? So right away you should see that the answer is 0. 5 is a constant. When you're taking the derivative of a constant without having to use the limit definition, we know right away from this theorem here, or this property, that the derivative of any constant is always 0. Okay, so don't fall for traps. Common traps here are, let's say this is example 1. Number 2, let's do it down here. If f of x is equal to pi, then f prime of x is also equal to 0. The derivative, pi is a constant, just a number. When you take its derivative, it's equal to 0. Third example, if they give us f of x is equal to, let's say the log base 8 of e to the pi, something like this. So again, it looks complicated, but notice that there's no parameter x. There's no x in this whole thing. This is just some value. It's a number. Log base 8 is a number. E to the pi is just a number. Log of a number is a number. So its derivative, although this may look complicated, it's just a constant. The answer is 0. Okay. Let's look at our next property. Okay, so the next property that we have here is called the power rule. So let n be an element of the real numbers. So n is just some constant. If f of x is equal to x to the n, then this implies that the derivative is equal to n times x to the n minus 1. Very important rule, we use this one very often. Let's take a look at the proof. So we'll start off with the simple case. We'll do case n equals 1. So essentially the function that you're working with is just f of x equals x. What's its derivative going to be? Well, let's go ahead and prove it. So f prime of x, again using the limit definition of a derivative, limit as h goes to 0 of f of x plus h minus f of x over h. So recall we're using the function f of x equals x. This means that the definition is limit as h goes to 0. Composition, if in the bracket instead of x we have an x plus h, this is side work. What's it going to be equal to? Well, whatever's in the bracket just comes here on the outside, so whatever's in the bracket is just equal to itself on the outside using this function. So what we get here is f of x plus h is essentially just x plus h, and then x, f of x is just x, so minus x, all this over h. So notice that the x's cancel, same numbers, opposite sign, and what we're left with is h divided by h, which is just 1. So limit as h goes to 0 of 1. There's no h in here, so as h goes to 0 doesn't affect this value, so the answer is simply 1. So does this stand with our statement up here so far? Let's check it out. So if we have f of x is equal to x, we showed that the derivative f prime of x is just going to be 1. Is that true? Well, up here what it says is that the derivative f prime of x, it's going to be n times x to the n minus 1. So essentially what we have is 1 in the exponent, and what we're going to do is take the exponent, what this is saying here, take the exponent and drop it in front. So the value in the exponent here is 1. We're going to drop it in the front, so we're going to put a 1 here. And then we're going to multiply by x, times it by x, and then in the exponent we're just going to subtract it by 1. So originally in the exponent we had n, and we're just going to subtract it by 1. So the n, in our case here, is a 1, so 1 minus 1 is 0, giving us 1 times x to the 0. And recall that any value to the exponent 0 is 1. So 1 times 1 is just 1, and that satisfies. It's equivalent to our proof. So this is done. So we showed the case where n equals 1. Now let's look at the case where, just the general case where we're using n in the exponent. Okay, so to prove the general case, what we're going to have to use is this formula here. There's different ways of doing it. The easiest way is probably using logarithmic differentiation, which we haven't learned yet, so I won't use that. We could also use the binomial theorem. That's another way of proving this. So the method I'm going to use is just using this formula here. So x to the n minus a to the n is equal to x minus a times x to the n minus 1 plus x to the n minus 2 times a plus dot 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 plus x times a to the n minus 1 plus no x a to the n. Oh, this is n minus 2 and this is n minus 1. Okay, that's better. Right. So this is the property that we're going to use in order to prove it. So let's go ahead and start the proof. So we're starting off with the derivative f prime of x, and what we get is the limit definition. We're just going to use the secondary limit definition. So not as h goes to 0, we're going to use the limit as x goes to a of f of x minus f of a over x minus a. Okay, and that gives us the limit as x, oops, not h, the limit as x approaches a, f of x, in this case here, f of x is x to the n, minus our f of a, which is substituting this with a, so instead of an x we put an a, we get a to the n over x minus a. And now you can see why we want to use this property here, because x to the n minus a to the n, which is what we have here in the numerator, gets transformed to all this. So I'm just going to substitute our property here. So we have x minus a in brackets times x to the n minus 1 plus x to the n minus 2 times a plus dot 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 x times a to the n minus 2 plus a times n to the plus a to the n minus 1. All this over x minus a. And the x minus a's cancel. Okay. And now we evaluate the limit. Substitute the, replace all the x's with the a's, giving us a to the n minus 1 plus a times n minus 2 times a plus dot 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 plus a times a to the n minus 2 plus a to the n minus 1. And notice that here we have the same base. So whenever you're multiplying the same base, you could add the exponents. This is a 1. This is a 1, same base, you add the exponents. So each term here has n minus 1. And how many numbers do we have in total? There's n numbers. Okay. So since they're all a to the n minus 1, because n minus 2 plus 1 is n minus 1, this gives us n times a to the n minus 1. So now that we proved the statement over here, let's go ahead and look at some examples. So if the function that's given is x to the 100, using the limit definition would take a long time. But using this property that we now have, this is a lot quicker. What we do is we drop the exponent, so the n comes here in front. So in the exponent we had 100, we drop it, multiply by x, and then subtract the exponent by 1. So 100 minus 1 is 99. And now we're done. That's the derivative. So now that we have these properties, we don't have to go through the limit definition anymore unless it specifically states to do it. We could just quickly apply these properties. Okay, so this is super useful. Another example, I don't know, let's go x to the e. This looks difficult, but it's the same concept. If you have to take the derivative, you drop the exponent, so x to the exponent e is just a number, we drop it, so e comes in the front, times x to the, and then we subtract the exponent by 1, so e minus 1, and we're done. Okay. We said this works for any number. Let's go ahead and try negative numbers. So what if we have x to the negative, I don't know, 3. Okay, just be careful with your negatives. If we have to take the derivative, we drop the exponent, so the negative 3 comes in front, times x to the, and then we subtract the exponent by 1. So if you put negative 2, be careful, you're subtracting by 1. Negative 3 times x to the negative 4. Don't leave your answer with negative exponents. So remember your laws of exponents. The negative causes the x to drop down. So we would write it as negative 3 divided by x to the 4. Okay. So this is the power rule, very important. We use this often, so make sure you're comfortable with this and you have this memorized. There's one more example where I want to take a look at roots. So two properties that we have to know. Let's just do square root of x, keep it simple. We have to know that a to the n is equal to, a to the negative n is equal to 1 over a to the n. So essentially if you have a negative exponent, you have to drop it. The other property you have to know is a to the, started this way, and m. If you have a root, a to the exponent m inside the nth root, you could rewrite it as a fraction. A to the m divided by n. So the m stays here on top and the nth root comes here on the bottom, and you can write it as a fraction a to the m divided by n. These are common properties that we often use, so keep these two in mind. So the one with the negative exponent we saw, we didn't see the one with the root. So whenever you have a root, switch it, change its form to a fraction. So the square root, there's really a 2 here, we don't write it, but we know it's there. And the exponent of the x is 1. So we could rewrite this as x to the, using this property here, the exponent comes here on top to the 1, the root, the nth root comes here on the bottom. So it's really x to the 1/2, and now we're ready to take the derivative of this because it falls into our power rule. It's of the form. So f prime of x, we drop the 1/2. Let me just erase this to give myself some room. We drop the 1/2 times x, and then subtract the 1/2 by 1. So 1/2 by 1 is negative 1/2. Again, negative exponents, we can't keep our answer like this, so we would rewrite this as 1 over 2 x to the 1/2. Or if you want to bring it back as a root, that's fine. You can rewrite it as 1 over 2 to the square root of x. And that's our answer. Okay, so the third property is the constant multiple rule. So let c be a constant, any real number, and g of x is a differentiable function, so the derivative of g of x exists. So if f of x is equal to c times g of x, this implies that the derivative, f prime of x, is equal to c times g prime of x. So essentially what this is saying is, if you have a constant in front of your function, you could essentially ignore it and just derive the function itself. Leave the constant. Okay. So let's see why this holds and take a look at the proof. So we begin with the derivative. So we're going to use the limit definition, limit as h goes to 0 of f of x plus h minus f of x, all this over h. Okay. So just recall, if f of x is equal to c times g of x, this means that f of x plus h is equal to c times g of x plus h. Essentially, whatever's in here replaces what's in here. So this guy moves into here, and that gives us the limit as h tends to 0. F of x plus h is this term, c times g of x plus h minus c times g of x. Okay, just following these two guys. All this divided by h. Okay. So now what we could do is, the numerator has a c, we could factor out the c, giving us the limit as h goes to 0 of c times g of x plus h minus g of x, all this over h. And then lastly what we could do is, since the limit just wants the h, the c is not affected by it, we could take this limit, the constant over here, and remove it from the limit. That's one of our limit properties, giving us c times the limit as h tends to 0 of g of x plus h minus g of x, all that over h. And all this over here is just the limit definition of a derivative, but now with respect to g instead of the function f. So this here is just equal to c times g prime of x. This is our definition. And this is the proof. We're done. Okay, so let's look at a couple of examples. Okay, so we'll work on these two examples. Try doing them on your own and then compare your answer with mine. So the first function we have up here is f of x equals 3 times x to the 20. So we're asked to find the derivative. F prime of x is, we ignore the 3, essentially that's what this tells us. Ignore the 3, leave the 3 in front, and just deal with the x to the 20. What's the derivative of x to the 20? Well, we saw this from our power rule, our second property, where we drop the exponent, so 3 times 20 times x, and then we subtract the exponent by 1, giving us 20 minus 1, which is 19. Okay, and then we can just end this by doing 3 times 20, which is 60, x to the 19. And this is our derivative. We're done. This one over here looks a bit more intimidating, but it's the same concept. We ignore the constant in the front, 5 over 4x to the negative 2/5. They could try to trick us and make this look a bit more complicated, something along the lines of, could have been given as 5 over 4x to the 2/5. These two guys are equivalent. So the constant, the 5 over 4, we pull it out, we get it over here. And the x to the over 5 is on the denominator, so we cannot use the power rule, because the power rule, we need it specifically of the form x to the n. You want x on the top. If you have a fraction and the x to the n is on the denominator, you can't use the power rule anymore. Okay, so be careful for that. Here you're forced to bring it up. Even though we don't like negative exponents, in this case we're forced to put it in this form. Now it's of the form to use power rule and the constant multiple rule, a combination of both. Okay, so it might look different. Sometimes you just have to manipulate it to set it up. But once you get it at this form, now we could take the derivative, giving us 5 over 4. I'm just going to keep it in the front. We're going to drop the exponent, giving us negative 2 over 5 x, and then subtracting the exponent by 1. So negative 2 over 5 minus 1. So without a calculator, you guys have to find a common denominator. 1, you could think of it as minus 5 over 5. This is work you do on the side. Negative 2 minus 5, you get negative 7 over 5. Okay, so in the exponent here, we have negative 7 over 5. Let me give myself room. So over here, notice that the 5's cancel. Negative 2 over 4 is negative a half. X to the negative, we said 7 over 5. So be careful, don't move your answer like this. You have a negative exponent, get rid of it. So we're going to rewrite this as negative 1 on top, and on the bottom we're going to have 2. We're going to drop the exponent as x to the 7 over 5. And this is the final answer. Negative 1 over 2 times x to the 7 over 5. So the next property that we're dealing with is the sum and difference rule. Let f and g be differentiable functions, so both their derivatives exist. If j of x is equal to f of x plus or minus g of x, then the derivative of j of x is equal to f prime of x plus or minus g prime of x. Essentially what this is saying is if you have an addition of two terms or a subtraction of the two terms, you could take the derivative of each term individually. Okay, so this is the idea. So let's look at the proof. The proof, I'm only going to do the positive case, the sum. The difference is the exact same procedure, so you'll be able to do that on your own. So for the sum, let's start off with our definition. So j prime of x. By definition, this is the limit as h tends to 0 of j of x plus h minus j of x, all this over h. Okay, so j of x plus h, essentially since j of x is f of x plus g of x, because that's what I'm doing the positive case, so j of x equals f of x plus g of x. When we talk about j of x plus h, what we're talking about is just removing the x's here and replacing them with x plus h's. So what we get here is the limit as h tends to 0 of f of x plus h plus g of x plus h minus, let me put this in brackets, our j of x, which is essentially just f of x plus g of x. Since there's a minus, I'm just going to put this in brackets. All this divided by h. So next what we do is we're going to just separate this. Put the f's with the f's and the g's with the g's. So essentially what we get is the limit of f of x plus h minus f of x. Because if we distribute this negative here, it hits both the f and the g. So we have f of x plus h minus f of x. I'm going to combine these two terms to get this. And then I'm going to take the g's and put g of x plus h minus g of x. So plus g of x plus h minus g of x. All this over h. Okay. And keep in mind, when you have fractions, 3 plus 5 over, let's say 2, what you could do is add the numerators, but you could also separate. This is only true if you have a plus or minus in the numerator. You could separate the terms. I think some teachers teach it as Hart method in high school. I don't know. You could separate the terms. So you can rewrite this as 3 over 2 plus 5 over 2. And that's the same idea of what we're doing here. This is our first term. Put in brackets. This is our second term. They're all being divided by h, so we're just going to divide each term by h. Okay, essentially we're using the Hart method that we learned in high school, or sometimes referred to as butterfly method. So we have the limit as h tends to 0 of f of x plus h minus f of x, all this divided by h, plus, and I'm also going to at the same time take the limit of both terms individually, just because I'm running out of room, so limit as h tends to 0 of g of x plus h minus g of x, all this over h. Okay. And what we get here on both sides is the limit definition. This is the limit definition of a derivative for f, this is the limit definition of a derivative for g. So this gives us f prime of x, we have a plus in the middle, and then this is g prime of x. So this shows that we showed that the derivative of j prime of x is f prime of x plus g prime of x, and we're done. And now you can do the exact same argument using the minus sign. So now with all these properties, what we're capable of doing is finding the derivative of any polynomial. Okay, because we did the power rule, the constant multiple rule, and the sum and difference rule. Okay. So putting everything together that we've seen, all these 4 properties, let's go ahead and find the derivative. So I'll let you guys work on this one on your own, see if you get the answer. So taking the derivative of this, you should get the first term, you ignore the 4, drop the exponent of the 5, and then subtract the exponent by 1. Minus 3 stays in the front, drop the 2, subtract the exponent here by 1, and the derivative of a constant negative 14 is 0. So we essentially just ended here. We have 20 x to the 4, 4 times 5 is 20, minus 3 times 2 is negative 6 x, and this is the answer. Okay. So we saw an easier example. Now let's continue and try this one. Find the derivative of this function using all the properties that we've learned today. Okay. So pause the video, attempt this on your own, and see if your answer matches mine. So the first thing that I see here is I'm going to switch this to be of the form x to the n, which here x to the 1/2 we have it, but this one here I'm going to manipulate it. So before I start deriving, I'm just going to I'm going to set myself up. So we have x to the 1/2 plus this, I'm going to write it as a fraction, plus 1/2. 1 over x to the 2 over 3, all this squared. And I still haven't derived yet, I'm just setting myself up. Now I'm going to bring this up, giving me x to the 1/2 plus x to the negative 2/3 squared. And again, we're still not done. Let's expand this. This thing squared is, and if you're thinking of distributing the 2 to the exponents, that's wrong. This is a binomial. This squared means you have to expand, you have to FOIL. So you should be thinking of it as x to the 1/2 plus x to the negative 2/3. You don't have to write all this down, but this is the way you should be thinking of it, plus x to the negative 2/3. Okay, and now we FOIL. So the first term that we get is x to the 1/2 times x to the 1/2. We get x to the 1/2 times negative 2/3 is plus x to the 1/2. It's the same base, so you're adding the exponent 1/2 plus negative 2/3. You have to find the common denominator. So the plus minus, you could just rewrite it as a minus. And this gives us 3. The common denominator is 6, 4, 6. Giving us negative 1 over 6. Okay. Now this term times, this times this, this times this, this times this is the same thing, plus x to the negative 1/6. And then the last term, negative 2/3 times x to the negative 2/3 gives us, you add them, so minus 4/3. No, minus 4, yeah, minus 4/3. Okay. So without even taking the derivative, all we did is set ourselves up. We now have x plus 2x to the negative 1/6 plus x to the negative 4/3. Okay. This is still the original function. Now the derivative f prime of x is, well, the derivative of x we saw is 1. The derivative of 2x to the negative 1/6 is plus 2 times, we drop the negative 1/6, subtract the negative 1/6 by 1, we get negative 7/6. And same thing here, plus we drop the negative 4/3, we get minus 4 over 3. x to the, and then subtract this by 1. So minus 7/3. Okay. Now we just have to simplify. No negative exponents, so we have the 1 in the front. This gives us minus 1/3. And then this is a negative exponent, so we drop it, x to the 7/6. And same here, minus 4 on top, 3 x to the 7/3. And this is the derivative. This is our final answer. So if you got this, good job. If not, keep practicing. Okay, so this is our last example. We have the function f of x equals x cubed minus 3x to the 1/2 plus 4 times x to the negative 1. All that divided by x to the 3/2. In the previous example, example 2, we saw a function which was squared, so it was the same term multiplying itself. We could have used a product rule, not the most efficient way of doing it, but that's something we haven't seen yet, so let's refrain from using that. Here we have a division, so you could use quotient rule if you've seen it, but try to solve it without using quotient rule. I think it's even easier without using quotient rule. So the technique here is to tackle each term individually. Okay, so when you have a division by a monomial, if we had a binomial on the bottom, this wouldn't work. We would be stuck using quotient rule. But if you have a monomial, one term on the denominator, deal with each term individually. Like we saw earlier, the Hart method. So what we're going to do is set ourselves up. So we're going to rewrite this as x cubed over x to the 3/2 minus 3x to the 1/2 over x to the 3/2 plus 4x to the negative 1 over x to the 3/2. Okay. And now what you're doing is the first term, you have the same base, x to the 3, x to the 3/2. When you have the same base and you're dividing, what do? We subtract the exponents. So you're doing 3 minus 3/2. So if you need to do this work on the side, because we're not allowed calculators, same base, so you multiply the top and the bottom by 2, so 6 over 2 minus 3 over 2, giving us 3/2. Okay, so this is just to show you guys how to do it without a calculator. I think this is fairly easy, giving us x to the 3/2. Here we have a constant, the minus 3, we're going to leave it, and then we're going to subtract the half minus 3/2, so let's do this on the side again. 1 minus 3, already the bases are the same, so you just subtract the numerators, giving us negative 2 over 2, which is just negative 1, so we have x to the negative 1. And then lastly, here we have our plus 4, we have our constant in the front, and then you're doing negative 1 minus 3/2, negative 1 minus 3/2, find a common denominator, minus 2 over 2, minus 3 over 2, giving us minus 5 over 2. Okay. So all this is the same function. We haven't taken the derivative yet. Okay, so we just set ourselves up to be in the form of, to apply power rule. Now we're ready to take the derivative. Okay, so make sure when you're doing this, at this stage you don't keep the equal sign. You have to state, like, at this stage you're taking the derivative, so we're going to write f prime of x. And the derivative of this, we drop the exponent using power rule, x to the 1/2 plus 3 x to the negative 2 and minus, what is that, 5 over 2 x to the negative 7 over 2. Okay, so the last step is just get rid of the negative exponent. So the answer here is going to be 3 over 2 square root of x, or x to the 1/2, plus 3 over x squared, and then minus 5 over 2 times x to the 7/2. And that's our final answer. Okay, so great work and keep practicing.